Imagine like waking up in this really spacious, affordable house. You've got a massive backyard and it's in Fresno, California.
Right.
You drink your coffee, you walk a couple blocks to a station, hop into this sleek levitating pod, and just 35 minutes later, you are stepping out into downtown San Francisco for your tech job.
Sounds pretty ideal.
It really does. I mean, you get the Silicon Valley salary, but you pay Central Valley real estate prices.
Yeah, that's the dream.
Today, we are unpacking a massive 2026 analysis on the future of infrastructure. And we're looking at a stack of sources that basically suggest this specific commute is not science fiction.
No, it's really not.
In fact, the technology to make it happen is already being built, just not in California.
Which is kind of the profound irony at the center of this entire analysis, right?
Oh, totally.
We have the stalled, just incredibly extensive reality of California's high-speed rail project. And it's sitting right next to the rapidly evolving open source promise of the Hyperloop. And to really understand how these two wildly different approaches to transit are colliding, we have to travel from, well, the concrete pillars of the San Joaquin Valley all the way over to a booming deep tech startup incubator in Chennai, India.
It's a huge shift. And before we get into the physics of, vacuum tubes and the billions of dollars at stake, I just need to give you a quick heads up on the framing of our sources today.
Right, the political side of it.
Exactly. The author of this analysis makes a very direct and honestly somewhat controversial link between the failure of massive infrastructure projects and the specific ways we elect our politicians.
Yeah, they really go after the electoral system.
They do. They argue that California's transit woes are a direct result of one-party dominance in the top two primary voting system. And they fiercely advocate for ranked choice voting as, like, the ultimate fix.
Which is a big claim.
Huge. So just to be clear, we are not here to endorse those political theories or take a side on how California should run its elections.
No, not at all.
Our goal is strictly to unpack the author's argument so you can see the fascinating hidden wires they're drawing between the ballot box and the transit station.
Because you really cannot separate the engineering from the environment it's built in. The political software of a state determined what kind of physical hardware actually gets constructed.
That's a great way to put it. So let's look at the hardware currently under construction. If we want to understand why alternative transit, like the Hyperloop, is suddenly looking so attractive, we have to diagnose the immediate crisis.
Right, it's a reality check.
Yeah, a harsh reality check on the California high-speed rail. I was looking back at the original 2008 voter initiative, Proposition 1A. The pitch to the voters was incredibly alluring.
Oh, it was a beautiful vision.
Right. It was a true dedicated bullet train connecting San Francisco directly to Los Angeles and Anaheim.
And the optimism back in 2008 was just palpable. You had this massive public mandate for green infrastructure. And the initial estimated price tag they presented to the public was roughly $33 billion, with, some of the more conservative upper-end estimates floating around $45 billion.
And they promised revenue service by 2020.
Right.
So for $40 billion, we'd be riding the train 4 years ago. But the 2026 reality documented in these sources is a completely different universe.
Completely different.
The latest draft business plan outlines what the state calls an optimized phase one. And I mean, whenever a government mega project uses the word optimized, no, it almost universally means heavily compromised to hide the financial bleeding.
It is a textbook euphemism. In this specific engineering context, optimized means they have completely abandoned the vision of a dedicated end-to-end dual-track system.
Wow.
Yeah, to save money, they are implementing single tracking in large portions of the Central Valley.
Which fundamentally breaks the promise of high speed. I mean, if you only have one track and you have northbound and southbound trains running simultaneously, one of those trains eventually has to pull over onto a siding and park so the other one can pass.
Exactly.
You are taking a vehicle designed to cruise at 220 miles per hour and forcing it into a perpetual game of yield.
And the financial kicker is that even with those massive operational compromises, even with the single tracking and the shared commuter corridors, this optimized phase one is now officially estimated at $126 billion.
It's just staggering. And if they wanted to actually build the train voters approved in 2008, the full dual-track, dedicated high-speed corridor from SF to LA.
Yeah, The sources indicate that full vision is now estimated at up to $231 billion.
That is nearly 7 times the original estimate.
It's hard to even wrap your head around.
But surely, I mean, if we've been working on this since 2008, there must be something functional, right?
Well, we can track the actual concrete poured. As of early 2026, roughly $13 to $15 billion has actually been spent, with about $23 billion in combined state and federal funding appropriated. That money went into the initial planning, the notoriously complex environmental reviews, land acquisition through the Central Valley, and building massive concrete viaducts.
Which you can actually see. Like, if you drive down Highway 99 today, you see these colossal Stonehenge-like pillars just standing out in the agricultural fields.
Right, but the glaring detail in the 2026 report is that zero high-speed track has actually been laid.
Zero.
After $15 billion, there is no revenue service. No one is buying a ticket.
And the timeline for actually buying a ticket keeps receding, doesn't it?
Oh, absolutely. The state's current focus is entirely on the initial operating segment, the IOS. This is just a 171-mile stretch in the Central Valley, connecting Merced to Bakersfield.
Okay.
Based on the 2026 projections, revenue service on just that isolated Central Valley segment won't begin until 2032 at the earliest.
So, 24 years after voters approved an SF to LA train, we might get a Merced to Bakersfield train. And the full connection to the coast.
Pushed out to 2040 or beyond. And honestly, that 2040 date assumes the state actually finds the money to finish it. Which brings us to the $90 billion funding gap.
Wait, $90 billion?
Yeah. Even for the cheaper, compromised $126 billion plan, there is no identified source for $90 billion of those dollars.
That is wild. And the traditional revenue streams are drying up, right? The sources point out that federal support has cratered, with $4 billion in federal funds actually rescinded back in 2025.
Right.
And the state's backup plan relies on cap-and-trade funding. From my understanding of the sources, cap-and-trade is essentially California's carbon market. Like, companies that pollute have to buy emission credits, and the state uses that money to fund green projects like the rail.
That is the mechanism, yes. It provides roughly $1 billion a year.
But $1 billion a year is a drop in the bucket when you need $90 billion just to finish the compromised version of the track. So if we just look at the mechanics of building things in California, why did the cost multiply by 7?
The author identifies a perfect storm of regulatory and logistical friction. You start with the California Environmental Quality Act, or CEQA.
Okay.
It allows virtually any local municipality, environmental group, or even competing business to sue to halt construction, demanding endless rounds of environmental impact reports.
Wow.
Then you layer on eminent domain.
Right. The government forcing you to sell your land for the train right of way.
Yes, and cutting a brand new, perfectly straight right-of-way through highly valuable, multi-generational agricultural land in the Central Valley, and then trying to weave it through incredibly dense urban environments in Los Angeles and the Bay Area. It results in thousands of individual drawn-out legal battles over property values.
I can't even imagine the legal fees. And then there's the geology, right?
Exactly. Trying to connect the flat Central Valley to the coast means punching through the Tehachapi Mountains. You are talking about boring massive tunnels through incredibly hard rock in an active seismic zone.
Which requires engineering tolerances that are wildly expensive.
You combine the tunneling, the litigation, the inflation that naturally occurs over a 20-year delay, and constant scope creep.
What do you mean by scope creep?
Where local cities demand the train authority build them new stations or grade separations just to secure their political support. You put all that together, and you reach that $231 billion ceiling.
So the author of our source material calls this the worst public infrastructure failure of our time.
Yes, they do.
But, you know, as someone looking at those concrete pillars in Fresno, I struggle with the idea of just walking away. We've already spent $15 billion. The land is bought. The bridges are built.
I know, it's tough to look at.
Right. If we stop now, that $15 billion is completely wasted. Doesn't it make more sense to just grit our teeth, accept the budget overruns, and finish the job we started? It's like budgeting 30 grand for a whole house remodel, spending 15 grand, and realizing you've only painted the hallway and the contractor now wants 200 grand to finish. Shouldn't we just finish it?
What you're articulating is the psychological grip of the sunk cost fallacy.
Right.
It's an incredibly powerful cognitive bias where we justify continuing a failing endeavor because of the resources we've already invested, rather than looking objectively at the future costs versus the future benefits.
So rational economics says that 15 billion is gone, whether we build the train or not. We have to make our decision based solely on the next 80 billion we are about to spend.
That is the strict economic view. And the author argues fiercely that throwing another $50 to $80 billion over the next decade into a truncated, heavily compromised Central Valley line represents a massive opportunity cost. That $80 billion is money diverted from immediate pressing needs. It could be used to massively subsidize high-density housing construction in a state paralyzed by a housing shortage.
That makes sense.
Or it could be used to completely modernize the existing local transit networks in LA and the Bay Area, which carry millions of daily commuters right now.
The argument is that because the current plan relies on blended operations, like forcing the bullet train to share tracks with slower commuter and freight rail, once it hits the urban centers, it delivers high speed in name only.
Exactly.
So the author is essentially screaming at California to stop throwing good money after bad. But if we abandon the high-speed rail, we still have 39 million people in a massive state, congested highways, and expensive short-haul flights. We need to move people.
Which forces a pivot to the alternative technological paradigms. The analysis transitions from the failure of conventional rail to a hard comparative look at the capital and operational realities of maglev and the Hyperloop.
Okay, so let's establish the baseline. Conventional high-speed rail steel wheels on steel tracks has one massive, undeniable advantage: brute force capacity.
Right.
A single train can carry anywhere from 500 to 1,500 passengers. If you run a train every 5 minutes, you are moving upwards of 12,000 people an hour in a single direction.
It is the ultimate mass mover.
Yeah.
And it is entirely proven. The Shinkansen in Japan has operated flawlessly since the 1960s. France has the TGV. China has built thousands of miles of it.
Yeah, the tech works.
The operational speeds are reliable, typically cruising between 125 and 220 miles per hour. But as we just discussed, the capital cost in the U.S. regulatory environment has effectively ballooned to over $200 million per mile.
So the next evolution up is maglev, or magnetic levitation. This removes the steel wheels entirely. You use incredibly powerful electromagnets to literally float the train above a guideway and propel it forward.
The immediate benefit is the elimination of physical friction. Without wheels grinding on rails, your track maintenance costs plummet, and your operational speeds can push past 300 to 375 miles per hour.
That's incredibly fast.
And it works. The Shanghai Maglev has been running a 19-mile route to their airport for years, and it cost them roughly $60 to $64 million per mile to build.
Which sounds like a bargain compared to California's rail. But we can't really compare Chinese construction costs with their state-controlled labor and land acquisition to building in the U.S.
No, not at all.
The sources look at U.S. maglev proposals, like the long-discussed line between Baltimore and Washington, D.C., and the estimates are completely astronomical. We are looking at $285 to $420 million per mile.
Yeah, the high cost is intrinsic to the maglev architecture. To levitate a massive, heavy train, you need an incredibly robust, precise electromagnetic guideway. It requires immense amounts of concrete, specialized rare earth materials, and complex power substations distributed along the entire route. You are building a continuous, high-voltage electromagnet the size of a highway.
So conventional HSR is proven but politically and financially bogged down. Maglev is faster and lower maintenance, but the upfront infrastructure costs are even more prohibitive.
Exactly.
Which brings us to the third option. And this one feels like it jumped straight out of a sci-fi novel. The Hyperloop.
Yes, the Hyperloop.
Elon Musk open-sourced this concept in his 2013 Hyperloop Alpha paper. You put a pod inside a sealed steel tube, you pump the air out to create a partial vacuum, and then you use magnetic levitation to shoot the pod through the tube.
By eliminating both physical friction with the track and aerodynamic drag from the atmosphere, you unlock theoretical speeds of 700 miles per hour or more.
And what really grabbed everyone's attention in 2013 was the price tag. Musk's Alpha paper estimated you could build the San Francisco to LA system for about $17 to $21 million per mile.
Right.
Now, looking at the 2026 data in our sources, that original estimate was highly optimistic. Modern estimates put Hyperloop construction anywhere from $50 to $120 million per mile.
But even at $120 million a mile, it is still potentially half the cost of California's conventional rail and a fraction of the cost of maglev.
And the sources explain why it's theoretically cheaper. It all comes down to the physical footprint. A conventional train requires a massive, wide, heavy track bed.
It takes up a lot of space.
But a Hyperloop tube is relatively small in diameter. You can elevate it on slender concrete pylons. This means you don't have to bulldoze entire city blocks or buy massive swaths of farmland, which radically reduces the eminent domain litigation we talked about earlier.
Furthermore, if you do have to go underground, say, through those notoriously difficult Tehachapi Mountains, the tunneling economics completely change.
How so?
Advanced tunneling firms, like the Boring Company, argue they can dig tunnels for less than 5% of the cost of traditional rail tunnels.
Wow, less than 5%. Because the tunnel only needs to be wide enough for a pod, not a massive double-decker train.
Precisely.
But looking closely at the Hyperloop's architecture, I see a glaring flaw when it comes to replacing conventional rail. We established that high-speed rail is essentially a massive public bus, moving thousands of people at once.
Right.
But the sources note that a Hyperloop pod only holds roughly 28 to 30 passengers. If HSR is a mass public bus, Hyperloop sounds like an exclusive fleet of Ubers zooming through a tube. How does that solve mass transit?
You are isolating the defining compromise of the entire Hyperloop paradigm. It fundamentally trades brute force mass capacity for extreme speed and lower infrastructure footprint.
Okay.
Because the per-pod capacity is so incredibly low, the only mathematical way to achieve meaningful throughput is high frequency.
High frequency. The sources say you would need to launch a pod every 30 to 120 seconds just to move a few thousand passengers an hour. Launching a levitating pod at 700 miles an hour every 30 seconds sounds like an absolute air traffic control nightmare.
It does. It requires a level of automated AI-driven precision that exceeds modern aviation. But the proponents of Hyperloop argue we are evaluating it against the wrong metric.
What do you mean?
It is not designed to be a high-capacity urban subway that stops at 10 different towns and moves millions of commuters locally. It is designed purely for point-to-point, ultra-fast regional travel.
Ah, I see.
The goal is to connect major economic hubs so seamlessly that they effectively become a single megaregion. But you are entirely correct that the unproven execution of scaling this technology safely, with pods launching every minute, is a monumental hurdle.
And the frequency of the pods isn't even the hardest engineering problem.
Yeah.
If this technology is so brilliant and theoretically cheaper to build, why isn't it everywhere yet?
That's the billion-dollar question.
The sources dedicate a massive amount of ink to the actual Achilles heel of the Hyperloop, maintaining the vacuum. This is where the futuristic theory smashes into the brutal reality of physics.
To achieve those 700-mile-per-hour speeds, you have to remove the air resistance. Pushing a train through the atmosphere at sea level at those speeds is like trying to run through waist-deep water. The aerodynamic drag requires an exponential amount of energy to overcome.
So you pump the air out, but the goal isn't a deep space, absolute vacuum, right? The sources mention a target pressure of roughly 100 pascals, or 0.75 torr.
That is roughly 1,000th of normal atmospheric pressure. It's a delicate balance.
Oh, so?
Well, if you drop the pressure to 100 pascals, you eliminate almost all the aerodynamic drag. But if you try to go further down to a hard vacuum, the efficiency of industrial vacuum pumps drops off a cliff.
Oh, I didn't know that.
Yeah, the energy required to suck out those last few molecules of air is astronomically high. So 100 pascals is the sweet spot.
In Musk's 2013 paper, he estimated the capital cost for all the vacuum pumps needed for a 350-mile route at a mere $10 million. But reading the modern engineering assessments, that number is almost laughable.
It grossly underestimated the fluid dynamics of a 350-mile tube.
Yeah.
You cannot just put a giant vacuum cleaner at one end in San Francisco and expect it to suck the air out all the way to Los Angeles.
Right.
You need distributed pump stations.
The sources mention vendors working with industrial pump companies to deploy systems like the DRIVAC and RUVIVAC, and to explain that without the corporate jargon, these aren't just big shop vacs.
Oh, not at all.
These are multi-stage, industrial-scale mechanical lungs. They use rapidly spinning rotors to literally trap molecules of air and forcefully eject them from the tube. And you need these massive pump stations spaced out roughly every 10 kilometers, about every 6 miles along the entire route to ensure redundancy.
When you calculate the cost of dozens of these containerized pumping facilities, complete with their necessary power substations, the capital cost scales up to tens or hundreds of millions of dollars for an intercity line.
But the upfront cost of buying the pumps isn't what kills the project. It's the cost of keeping them running. Because you are trying to maintain a near vacuum inside hundreds of miles of steel tubing, and that tube is sitting outside in the elements.
It is essentially a 350-mile-long pressure vessel, and a steel tube of that magnitude has thousands of welded joints. It has massive airlock stations where the pods enter and exit.
And the environmental stress in California is extreme. In the Central Valley, the sun beats down during the day, heating the steel. Steel expands when it gets hot.
It does.
A 350-mile steel tube will literally expand and contract by several feet every single day as the temperature changes.
That constant thermal expansion and contraction puts immense stress on every single weld and seal.
Yeah.
Then you add in the constant microseismic vibrations of living in earthquake country.
So it is inevitably going to spring microscopic leaks.
Yeah.
It's like trying to keep a 350-mile-long bicycle tire perfectly deflated while poking it with invisible needles, and there are earthquakes happening.
Exactly. The in-leakage is unavoidable. Gases will even naturally desorb from the interior surface of the steel itself.
Wait, the steel itself releases gas?
Yes. Because of this constant intrusion of air, the vacuum pumps cannot just be turned on once to suck the air out and then turned off. They must run 24 hours a day, 7 days a week, constantly fighting the atmosphere just to maintain that 100 Pascal equilibrium.
And fighting the atmosphere requires electricity. The sources reference a study modeling a Hyperloop route on the scale of Amsterdam to Paris. They calculated that continuous vacuum pumping alone would consume roughly 516 megawatt hours per day.
If we translate that energy load into a California context and apply industrial electricity rates of roughly 10 to 20 cents per kilowatt hour, running those pumps costs anywhere from $10,000 to $60,000 per day.
Up to $60,000 a day, just for the electricity to run the vacuum pumps.
Which translates to roughly $3.6 to $22 million a year on a single major route.
That's a huge chunk of change.
And that figure strictly covers the electricity. It does not account for the localized labor needed for maintenance, replacing the massive pump components, or the complex AI sensor network required to instantly detect and locate a micro leak across hundreds of miles of steel.
When you say $22 million a year just for vacuum electricity, it sounds like a fatal flaw. But the sources make a really fascinating counter-argument here about the nature of infrastructure costs.
They do.
It's not that the Hyperloop is necessarily creating a new cost burden. It's that it is completely shifting the nature of the expense.
It is a fundamental shift from physical wear to energy consumption. Think about the maintenance budget for conventional high-speed rail. You have a staggeringly heavy train smashing over steel tracks at 200 miles per hour.
Right.
The kinetic energy and physical friction are immense.
You have to constantly bring in specialized grinding trains to re-smooth the rails. You have to routinely replace the steel wheels on the trains.
And you have to maintain the overhead catenary wires that supply the electricity. Those wires are exposed to wind, rain, and the constant violent physical friction from the pantograph on top of the train scraping against them. Maintaining physical rail infrastructure costs billions of dollars over decades.
But the Hyperloop pod is magnetically levitating in a near vacuum. There is literally no physical contact between the vehicle and the tube.
Precisely. The physical wear and tear is virtually eliminated. So instead of spending your maintenance budget replacing ground-down steel rails and shredded copper wires, the Hyperloop spends its maintenance budget entirely on energy, sealing, and leak monitoring.
It's trading a materials expense for an energy expense. But even if $22 million a year is cheaper than replacing steel rails, where does all that electricity come from? I mean, the whole point of modern transit is to be green.
The original vision proposed layering the top of the entire steel tube with solar panels. Over a 350-mile stretch in sunny California, the sheer surface area of those panels could theoretically generate more power than the pumps and the propulsion systems consume, making the entire system net energy positive.
But relying purely on solar introduces a massive vulnerability. We talked about how the pumps have to run 24/7 to fight leaks. The sun goes down every night. And what happens if a section of the tube suffers a major breach, like a seal failing, and floods with atmospheric air?
Re-evacuating a flooded section of the tube doing a full pump down from atmospheric pressure back to 100 pascals requires a massive, sudden spike in energy demand that solar panels alone cannot handle.
Right.
You would absolutely require monumental battery storage banks at every single pump station, or incredibly robust, high-capacity connections to the main electrical grid to handle those peak loads.
So the vacuum challenge is undeniably massive. And it explains why, despite all the glossy renderings and the theoretical cheap construction costs, no one in the West has actually built a commercial Hyperloop. We are looking at a landscape of stalled efforts.
The global context in 2026 is sobering for Western tech companies. Virgin Hyperloop, which eventually transitioned into Hyperloop One, was the loudest voice in the room.
Yeah, I remember them.
In November 2020, they achieved a massive PR milestone. They actually put 2 human executives into a pod and launched them down a 500-meter test track in Nevada, hitting about 107 miles per hour.
I remember seeing the footage of that. It felt like the future had arrived, but then they completely stalled out.
They collided with the harsh reality of human safety certification. Proving that a pod can levitate in a vacuum for 500 meters is an engineering problem. Proving to a government regulator that you can safely transport hundreds of humans at 600 miles per hour through a depressurized tube is a regulatory nightmare.
I can only imagine. You have to design aerospace-grade life support systems for the pods. You have to invent fail-proof emergency evacuation protocols in case a pod gets stranded in a vacuum. The sheer cost and complexity of certifying human safety in that environment broke their momentum.
Consequently, they pivoted away from passenger travel entirely to focus on cargo, laid off a significant portion of their staff, and faced massive internal setbacks.
Wow.
Other Western companies, like Heart Hyperloop in the Netherlands, are making slow, methodical progress. They are testing vital infrastructure components, like high-speed track switching at the European Hyperloop Center, but they are still years away from commercial revenue service.
So the West proved the fundamental physics, the levitation, the propulsion, the vacuum, but they hit a massive wall when it came to scaling and safety certification.
Exactly.
But the sources don't dwell on the Western failure because there is a massive breakthrough happening on the other side of the planet. While the American companies are stalling out, a startup in India just decided to bypass the hardest parts entirely.
Enter TuTr Hyperloop. This is a deep tech startup incubated out of the Indian Institute of Technology Madras, or IIT Madras, which is effectively the MIT of India.
And the timeline here is incredibly aggressive. They were only founded in 2022.
True, but their institutional knowledge runs deeper. The founders emerged from the Avishkar Hyperloop student team, which was formed back in 2017.
Okay.
These engineering students prove themselves on the global stage, ranking in the top 10 at SpaceX's rigorous Hyperloop pod competition and placing in the top 3 at European Hyperloop Week.
So you have this cohort of brilliant engineers who have already spent years iterating physical prototypes, and they decide to commercialize it. The sources highlight Dr. Aravind S. Faradwaj, the CTO, and Balaji Rangachari, the CEO, driving this with the deep academic backing of propulsion experts at IIT. And they aren't just making 3D animations.
No, they're pouring concrete.
Yeah.
By December 2024, TuTr completed Asia's first Hyperloop test track facility at the IIT Madras Discovery Campus. It is a 410-meter vacuum tube, and they are targeting test speeds of 200 kilometers per hour.
But a 400-meter university test track, while impressive, isn't a commercial product. The real bombshell in this 2026 analysis is what TuTr achieved shortly after that.
They secured the world's first commercial intent deployment of Hyperloop technology. They signed a contract worth roughly $1 million with the Deendale Port Authority in Kandla.
Wait, really? A seaport? Why is a seaport buying a Hyperloop?
Well, because they aren't trying to move business commuters between cities, they bought an automated cargo mover. The port intends to use the electromagnetic tube technology to move massive 40-ton steel shipping containers from the unloading berths to inland warehousing zones a few kilometers away.
And this completely short-circuits the regulatory nightmare that killed the American companies. A 40-ton steel box full of televisions doesn't need to breathe. It doesn't need an aerospace-grade life support system.
Exactly.
If a cargo pod suddenly loses power and stops in the middle of a vacuum tube, the Port Authority doesn't have a mass casualty event. They just have a delayed shipment.
By focusing explicitly on a freight-first pragmatism, TuTr bypasses the entire human safety certification quagmire. Furthermore, by operating entirely within the private jurisdiction of a port authority, they avoid the decades of eminent domain lawsuits and public environmental reviews that paralyze intercity public transit projects.
It is brilliant. They isolated the core physics of the Hyperloop and stripped away the biological and political complexities, and it immediately solves a real-world economic bottleneck. Anyone who remembers the supply chain crisis knows that moving containers out of congested ports is a multi-billion-dollar problem.
Oh, absolutely.
TuTr is getting paid real money to solve a real logistics problem today, using their technology at slower speeds over short distances.
You can clearly see the parallels to the early strategy of Tesla. Tesla didn't try to build the affordable mass-market Model 3 as their first car. That would have required billions in manufacturing infrastructure and economies of scale that a startup simply didn't possess.
Right. Tesla built the Roadster first. It was expensive, low volume, and aimed at a niche market of rich early adopters. But selling the Roadster generated the critical revenue and real-world engineering data they needed to survive and fund the development of the Model S and eventually the mass-market cars.
TuTr is running the exact same playbook in the infrastructure space. They are building a heavy, slow cargo mover first, generating revenue from port authorities, and using that controlled environment to master the vacuum sealing and propulsion at scale.
It makes so much sense.
The sources contrast this pragmatic, iterative approach directly with the all-or-nothing visions of Western companies who tried to raise billions to jump straight to a high-speed passenger line on day one.
And TuTr's endgame is still passenger travel. The sources outline their roadmap. They have a memorandum of understanding to build a much larger port connectivity system, linking the Jawaharlal Nehru Port Trust to the Vadhavan port. But the real leap is a planned 40 to 50 kilometer test track, heavily backed by Indian Railways, designed to evaluate the system at a full 600 kilometers per hour.
If they can successfully scale the vacuum technology and prove the safety systems on a 50-kilometer cargo track at full speed, they will have the definitive data needed to finally approach human passenger certification. Their ultimate stated goal is an ultra-fast inner-city passenger corridor, like connecting Chennai to Bengaluru in roughly 30 minutes.
Now, to maintain our analytical rigor here, we have to acknowledge the massive risks that still exist. Moving a shipping container 2 kilometers inside a flat port does not prove you can build a 350-mile vacuum tube across an earthquake fault line. Scaling the vacuum maintenance and managing thermal expansion over difficult terrain remains entirely unproven at commercial scale.
The engineering hurdles haven't vanished, but TuTr's methodology gives them a vastly higher probability of actually surviving long enough to solve them. And they have one other massive advantage that the sources emphasize: government synergy.
Right. TuTr isn't fighting the government. They are incubated by it. They are deeply backed by the Ministry of Railways and aligned with massive national initiatives like Make in India and the push for total self-reliance. The Indian government is actively providing the funding, the testing grounds, and the regulatory runway for them to experiment.
Which forces us to look back across the ocean to California. We now have an emerging, theoretically viable technological alternative in the Hyperloop. And thanks to India, we have a proven, pragmatic execution model. Partner with the government, start with freight in controlled environments, and iterate.
So if TuTr proves the physics and the economics of freight first makes sense, why is California still pouring billions of dollars into concrete pillars for a 200-mile-per-hour train that is heavily compromised and functionally bankrupt?
This is the exact pivot point of the 2026 analysis. The author argues emphatically that California's inability to build modern transit or pivot to new technologies is not an engineering failure. It is a systemic political failure.
And again, a quick reminder to our listeners, we are stepping into the author's specific political critique here to understand their theory of change. We aren't endorsing these conclusions, just reporting the connections they draw.
The author views the $126 billion high-speed rail disaster as the ultimate symptom of a broken governance model. They argue the project has been captured by deeply entrenched interest groups, specifically pointing to powerful labor unions and entrenched consulting firms who benefit financially from the endless construction and planning phases, regardless of whether a train ever actually runs.
And the author traces the root cause of this lack of accountability directly to the ballot box, specifically criticizing California's current election system, the top two open primary. Let's walk through how this actually works mechanically. California voters approved this back in 2010 under Proposition 14.
The mechanism is straightforward. Instead of Republicans and Democrats holding separate primary elections to choose their respective nominees, every single candidate for an office, regardless of party, is thrown onto one massive primary ballot. Every voter receives the exact same ballot. The two candidates who receive the most votes advance to the general election in November, even if they belong to the same political party.
The theoretical goal behind Prop 14 was moderation. The idea was that in a heavily progressive district, you might end up with two Democrats facing off in November. And to win that general election, one of those Democrats would have to moderate their platform to appeal to the conservative and independent voters in the district, pulling the entire legislature toward the center.
And political science data does suggest it achieves some of that intended moderation. However, the author highlights a massive, glaring flaw in the system: the extreme risk of vote splitting.
Let's construct a hypothetical race to explain vote splitting. Imagine you have a race for governor in a state where 60% of the voters lean progressive and 40% lean conservative. You have a crowded primary ballot. 5 really strong, charismatic, progressive candidates jump into the race. They end up splitting that 60% progressive vote perfectly evenly, meaning each progressive candidate only gets 12% of the total vote.
Meanwhile, the conservative side is highly disciplined. Only 2 conservative candidates enter the race. They split their 40% of the electorate evenly, getting 20% each.
So when the polls close, the 2 conservative candidates finish in first and second place with 20% each. All 5 progressive candidates are eliminated with 12%. The general election in November is now between 2 conservatives, in a state where a clear 60% majority of the voters are progressive.
The majority accidentally fragmented themselves and allowed a minority faction to sweep the primary. This fear of vote splitting is so pervasive that it actively discourages new, innovative candidates from running. Party bosses will aggressively pressure people to drop out of races to avoid splitting the vote.
That makes sense.
Because of these systemic flaws, the sources note there is actually a major ballot initiative slated for May 2026 attempting to repeal the top 2 system entirely.
So if top 2 is fundamentally flawed by vote splitting, what is the author's proposed solution? How do we fix the ballot?
The author is a staunch advocate for ranked choice voting, or RCV, which is also known as instant runoff voting.
And from my reading, RCV essentially functions as an insurance policy against throwing your vote away. Under this system, when you walk into the voting booth, you don't just pick one name. You rank the candidates in order of your actual preference: first choice, second choice, third choice, and so on.
When the polls close, the election officials count up all the first choice votes. If any single candidate secures over 50% of the first choice votes, it's a clear majority, and they win the election immediately.
But the magic happens when there are 5 candidates and the vote is fractured and nobody hits that 50% threshold.
That triggers the instant runoff. The officials look at the candidate who received the absolute fewest first-choice votes, and they eliminate them from the race. But if you were a voter who picked that losing candidate, your ballot doesn't go in the trash. Your vote is simply transferred to whoever you marked as your second choice.
So you get to vote for your absolute favorite pie-in-the-sky fringe candidate without any fear. Because if they lose, your vote just automatically slides over to your more mainstream backup option.
Exactly the intent. The officials recount the totals with the transferred votes. If someone crosses 50%, they win. If not, they eliminate the next lowest candidate and redistribute again. They repeat this cycle until one candidate proves they have the broad consensus support of a majority of the voters.
And the sources point out that this isn't just a theoretical exercise. In over 60% of U.S. ranked choice races that feature 3 or more candidates, the election actually requires multiple rounds of counting. Which means that under our old system, 60% of those elections would have crowned a winner who was actually opposed by a majority of the voters. Our CV forces a mathematical consensus.
And it triggers a profound psychological shift in how politicians behave. In an RCV system, a candidate knows they probably won't win on first-choice votes alone. They desperately need the second-choice votes from the supporters of their opponents.
Which completely changes the campaign strategy. You cannot run a vicious, scorched-earth smear campaign against a rival candidate if you are simultaneously begging that rival's supporters to rank you second on their ballot.
The data strongly supports this. Studies show RCV leads to measurably more civil issue-focused campaigning. The sources also highlight a roughly 17% increase in municipal voter turnout where RCV is implemented, and significantly higher win rates for women and minority candidates because they no longer face pressure from party insiders to wait their turn to avoid splitting the vote.
But the sources do acknowledge some downsides to RCV, right? It isn't a magical cure-all.
It has caveats. The most prominent is ballot exhaustion. If a voter is confused by the system or just stubborn and only ranks a single candidate, their ballot becomes exhausted and stops counting if that candidate is eliminated in an early round. There are also concerns about the sheer complexity of asking voters to research and rank half a dozen candidates, and some data shows it can lead to a short-term surge of lower-quality candidates jumping into races simply because the barrier to entry feels lower.
Okay, I understand the mechanics of vote splitting and instant runoffs, but this is the moment where I have to step back and challenge the core premise of this entire analysis.
Okay, go for it.
We just spent an hour talking about the fluid dynamics of vacuum tubes, the thermal expansion of steel, and the multi-billion-dollar cost of boring tunnels through mountains. RCV sounds like a fantastic way to make local mayoral debates more polite. But how does changing the math on a ballot translate to pouring concrete cheaper?
That's a fair question.
A bloated, multi-year environmental review process exists regardless of whether a state senator won by a plurality or an instant runoff. How does a new ballot actually fix a broken train?
It is the crucial question, and it requires understanding the author's theory of change regarding political incentives. Why hasn't California aggressively audited or canceled the high-speed rail, despite a price tag inflating from $33 billion to $126 billion?
Because politicians don't like admitting they made a $100 billion mistake.
That's part of it, but the structural reason is fear. In a heavily gerrymandered one-party state, or a system constrained by top two dynamics, an incumbent politician in a safe district is functionally immune from losing a general election.
Okay.
Their only real threat is a primary challenge from the extreme fringe of their own party, or losing the financial backing of the powerful interest groups like the construction unions and consultants who are benefiting massively from the ongoing rail project.
So they just keep voting to fund a failing project because standing up and screaming, "Stop," would make powerful enemies and invite a primary challenger.
Yes, they are trapped by the incentives of the system. But if you implement ranked choice voting combined with open primaries, the math changes. A politician can no longer win simply by pandering to an extreme, vocal minority faction. To secure those vital second and third choice transfers, they are forced to build a broad coalition of moderate pragmatic voters.
And the author's theory is that when politicians are no longer terrified of their extreme flank, they suddenly gain the political cover required for true accountability.
Precisely the argument. The author believes RCV incentivizes politicians who prioritize practical execution over ideological signaling.
Yeah.
A government elected via RCV, theoretically, has the courage to stand up and admit a megaproject has failed.
That would be something.
They have the political safety to demand independent, ruthless cost-benefit audits. They gain the ability to actually fire underperforming, entrenched contractors.
They gain the humility to say, we screwed up the train, let's cut our losses and look at what the private sector or a startup in India is doing with the Hyperloop.
That is the direct line the author draws. Electoral reform changes the incentive structure of the politician, which gives them the courage to embrace disruptive innovation and abandon sunk costs.
Okay, let's play this out to its logical conclusion. Let's assume for a moment that this grand alignment actually happens. The 2026 ballot initiative passes, California implements RCV, the newly accountable legislature caps the bleeding on the high-speed rail, and they launch an aggressive, competitive bid to bring Hyperloop technology to the state, starting with cargo pilots, just like TuTr did. If they actually build the tube, what is the ultimate payoff for the average resident? How does this fundamentally alter the listener's daily life?
The ultimate payoff, according to the analysis, addresses the single most destructive economic and social force in California today.
The housing crisis.
The housing situation is brutal. The sheer cost of living on the coast in San Francisco, Silicon Valley, and Los Angeles is actively suppressing economic growth, hollowing out the middle class, and fueling a devastating, intractable homelessness crisis. The root physics of the housing crisis is a geographic mismatch between high-paying jobs and available land. The massive economic engines of tech and entertainment are clustered on the coast. People desperately want to work there, but they cannot afford to live within a reasonable commuting distance.
And the traditional urban planning solution is to try and force massive, high-density zoning building skyscrapers into those fragile, already overcrowded coastal areas, which triggers intense, years-long legal resistance from local neighborhoods who don't want the density.
But if you look slightly inland, the Central Valley cities like Merced, Fresno, and Bakersfield has vast, sprawling amounts of developable, relatively affordable land.
Yes, but it's geographically isolated. You cannot commute 3 hours each way in gridlock traffic from Fresno to San Francisco every single day. The distance breaks the utility of the land.
But introduce an ultra-fast point-to-point Hyperloop into that exact equation.
You collapse the geography. If you can travel at 500 or 600 miles per hour, suddenly a reliable 35-minute pod ride turns Fresno from a distant agricultural hub into a highly accessible, hyper-viable commuter suburb of Silicon Valley.
The author describes this as dispersed density. A coastal worker, a nurse, a teacher, a mid-level tech employee could buy a spacious, affordable home with a yard in the Central Valley, hop in a pod, and be at their job in downtown San Francisco faster than someone trying to drive across the Bay Bridge in morning rush hour.
You solve the coastal housing crisis not by forcing skyscrapers into San Francisco, but by making the inland regions instantly accessible.
And the economic multiplier of that geographic compression would be staggering. If the state pairs this transport infrastructure with aggressive, transit-oriented zoning reform around the inland stations, it would trigger a massive housing construction boom in the Central Valley. You would see secondary tech hubs clustering around the stations, localized double-digit GDP growth as construction explodes, and a massive expansion of the state's tax base.
The sources outline a very specific three-step action plan to trigger this boom. Step 1. Acknowledge the HSR sunk costs and strictly cap the state's financial exposure to stop the bleeding.
Right.
Step 2. Pass the governance and electoral reforms like RCV to ensure political accountability. Step 3. Launch a competitive, transparent Hyperloop procurement process open to global innovators like TuTr and the Boring Company, starting with low-risk cargo pilots in the Central Valley to prove the tech.
It is a sweeping, transformative vision.
But I have to push back on this vision of a Central Valley utopia, because it sounds like we're just exporting our problems. If we suddenly connect Fresno directly to Silicon Valley salaries, the real estate market in Fresno is going to explode. Aren't we just exporting coastal gentrification, displacing the current working-class residents of the Central Valley who currently rely on that lower cost of living?
That is the most potent, realistic critique of the dispersed density model. If you flood a cheaper market with high-earning commuters, prices will inevitably rise, and displacement is a severe risk. You cannot ignore the gentrification threat. However, the counterargument lies in the sheer scale of the geography.
Walk us through the geographic scale.
The San Francisco Peninsula is a severely constrained, narrow strip of land surrounded by water on three sides. It literally has no physical room to grow outward. It can only grow up, which is expensive and politically difficult. The Central Valley, conversely, is a massive, sprawling agricultural plain. It possesses an order of magnitude more developable land.
So the argument is that the Central Valley actually has the physical space to build enough new housing supply to absorb the massive demand, whereas the coast physically cannot.
Correct. If local Central Valley governments proactively zone for massive high-density development before the Hyperloop stations open, they can theoretically increase housing supply fast enough to manage the price increases and mitigate the hypergentrification we see on the coast. But pulling off that kind of proactive, coordinated zoning requires exactly the kind of competent, forward-thinking, accountable governance that the author argues is currently missing from the system.
Which brings the entire analysis full circle. The author's ultimate conclusion is incredibly stark. It asserts that basic political integrity demands admitting the $126 billion high-speed rail failure, and that a healthy dose of humility should open the door to partnering with global innovators like a startup incubated by students in India to actually build the future of California.
It is a demand for a fundamental rewrite of both the physical and political infrastructure of the state.
Let's take a breath and recap the incredible, multifaceted journey of this deep dive. We started by confronting the staggering $126 billion reality of a California rail project that, after 15 years and $15 billion spent, still hasn't laid a single mile of high-speed track.
We weighed the brute force, proven mass capacity of traditional trains against the futuristic 700-mile-per-hour promise of the Hyperloop. We dove deep into the brutal physics of that promise, the sheer daily energy cost of running industrial mechanical lungs to maintain a vacuum against the relentless pressure of the atmosphere and the thermal expansion of a 350-mile steel tube.
And we contrasted the stalled, overregulated efforts of Western tech companies with the incredible, pragmatic rise of India's TuTr Hyperloop. We saw how they're completely bypassing human safety regulations by focusing on port cargo, putting steel in the ground, and proving the physics while generating actual revenue.
And finally, we tracked how all of this physical infrastructure is inextricably tied back to the ballot box. We explored the provocative argument that changing the mathematical mechanics of how we vote, shifting from the vote-splitting dangers of top two primaries to the consensus building of ranked choice voting, might just alter the psychological incentives of our politicians.
Giving them the political cover and the courage to abandon sunk costs, embrace disruptive innovation, and build a transit system that could actually solve the California housing crisis by turning the vast Central Valley into an accessible commuter paradise.
It is a remarkable synthesis of civil engineering, fluid dynamics, economics, and political science. It highlights a universal truth. The barriers to human progress are rarely just technical. They're deeply, stubbornly human.
Think back to the image we started with, the idea that big infrastructure is solid, permanent, like a concrete viaduct standing in a field. We realize now that the concrete is incredibly fragile, entirely dependent on the political software running the system. So we want to leave you with a provocative thought to mull over as you go about your day.
Yeah, think about this.
If a developing nation like India can rapidly build out the physical future of transportation by focusing on humble, practical cargo pilots in its ports, are Western megaprojects permanently handicapped by their own pursuit of perfection, political signaling, and endless environmental studies?
It's a great question.
The technology to collapse geography and travel at airline speeds on the ground exists today. The real question is whether our political software is capable of running it.
That is the ultimate test of the infrastructure of tomorrow.
Thanks for joining us on this deep dive.